everyone. This is the lecture for section 3.4, partial fractions. So in this section, what we're going to be really looking at today is integrals that have some form of a rational function in them. If you remember from pre-calculus, something that has a p over q, where both p of x and q of x are polynomials, right? And q of x, right, can be either reducible or irreducible. We can sort of factor them out or not, right? So these are the particular functions that we're going to be looking at today, in particular how to take the integral for them, okay? So let's go ahead and get started. Right off the bat, I'm going to have you guys do a quick check, right? This one deals with just non-repeating linear factors, right? So these are supposed to be really quick right now, right? At this point, it's a simple U substitution, and they're all going to have a bunch of ln's in it, okay? So go ahead, try these out, okay? And get some answers for them, cool? And what I want to do next is, so in the next quick check, flat out, real quick, you guys are doing another quick check. For quick check number 2, I just want you guys to do the common denominator. So basically, I want, so what I want you guys to all do for both of these is give me an equal to something, right? Where something is on the bottom, right? And something is on the top, completely expanded out, right? Okay, now, if you guys take a look right below, right, I give you what they're supposed to be, right? So this right here is supposed to be this right here. Okay, and then this right here should be this right here. Okay, so just double check, make sure that you get the right solutions for both of them when you do the common denominators and completely FOIL and you know, expand it all out. Give me the nasty fraction that you're going to get. Okay, so in the quick check above, right, you should have gotten this for both of them, right? Each one of you guys, everybody's doing either an odd or an even problem, right? So I'm giving you the solution to it, right? So there's two things that I want you guys to sort of observe from the two quick checks that I did. Okay, the first one is that both quick checks in quick check 1, right, were easily solved using U substitution. That's all we needed, right? And we needed just the basic logarithm. The integral of 1 over x is just ln of x, right? Okay, and the second thing that I wanted you guys to notice, right, is that right here, these two integrals right here, this one, right, and this one, okay, there is an x squared on the bottom of both, right? But there is no derivative for it anywhere. So in order for us to use U substitution for one of these, we need to have the derivative also show up somewhere, right? In both of these integrals that I'm showing you guys right now in the middle of the page here, neither one of them can be solved using U substitution because the derivative is nowhere in there, right? So we have to figure out another way to solve these, right? Now, I gave you the breakdown. Okay, and those breakdowns are these, the things in green that I'm highlighting right now. Okay, those are the breakdowns. So how can we get those breakdowns, right? That is the point behind this section. It is called the partial fraction decomposition. We are essentially undoing common denominators. That is what this process does, okay? And what it does, at least for calculus, right, is it breaks down these rational functions into something that's much simpler for us to use calculus on, okay? So that's what we're going to do today. And I'm going to go ahead and do an example. So you know what the result's supposed to be, right? I've already sort of given you guys the answer for the quick checks up above, right? And you know what the process is supposed to be, right? So I'm going to go ahead and do one and show you guys how this is supposed to go about, okay? And overall, right, for this section in particular, the theory matches all the way down, okay? And it's just different flavors of it once I show you what we're doing, okay? So what I'm going to do here is I'm going to perform the partial fraction decomposition for the following expression. So I'm going to try to break this apart, Okay, I'm going to try to break this apart into two fractions, right? So the way that I'm going to do that, first of all, is this. 2x minus 16, I'm just going to rewrite the top. The bottom, I know that factors. That's going to be an x plus 2, x minus 2. Okay, now here comes the sort of like the important bit of the theory, the thing that carries on for the rest of the section. Okay, I can break this up into two fractions, right? One of them has to be x plus 2, right? Plus another one that has to be x minus 2. I don't know what goes on top, but something has to go up above it, right? And at the moment, I know it has to be constants, okay? So this is basically the whole section right here, okay? And now I'm gonna redo my common denominators just with this right here, just with this bit right here, right? So if I do my common denominators again, right, just to collapse it back down, I should get something like this, right? A times x plus 2, whoops, sorry, x minus 2, plus b x plus 2, right, over x plus 2, x minus 2. So if you do common denominators, right, this is what you should get. Okay? And all of this, right, has to be equal to 2x minus 16 over x plus 2, x minus 2. Okay? So it stands to reason, right, that if you guys take a look, right, the bottoms are already equal, right? So therefore, the tops must be equal. So continuing from this step, we know that a x minus 2 plus b x plus 2 has to equal to 2x minus 16. So then I'm going to expand the left-hand side. It's going to be a x minus 2a plus bx plus 2b has to equal to 2x minus 16. Okay. I'm going to collect the stuff with the x's and the numbers on the left-hand sides, and I'm going to produce this, a plus b x minus 2, a minus b is equal to 2x minus 16, right? So therefore, right? Oh, look at me go. You guys got to see the notes. It stands to reason, right, that the x's should be equal and the numbers should be equal, right? So that means a plus b has to equal 2, and minus 2 a minus b has to equal to negative 16, right? From the first equation, we get that a is equal to 2 minus b, and we get to use that in our second equation. So if you take a look, right, minus 2, my a is 2 minus b, so it's going to be, follow along, right? So 2 minus b has to equal to negative 16. Okay, that means 2 minus b, 2, I can divide the whole thing by 2, so this gives me 8, right? I'm going to go ahead and distribute all of this stuff, so you get minus 2b plus 2 is equal to 8, right? Minus 2b, that's a plus there, right? Minus 2b is equal to 6, so b is equal to negative 3. And since b is negative 3, right, a has to equal 5. So then that means that my original statement, right, my 2x minus 16 over x squared minus 4, that is also equivalent to 5 over x plus 2 plus negative 3 over x minus 2. And we are done. We have broken up a common denominators. You guys notice that, hopefully. The original statement was already common denominators, right? And we broke it up into two separate fractions, right? That's the power of partial fractions decomposition. Okay, so these are the same, two of them, right? The top two are the same problems that you were doing in the quick checks from up above, right? Now it's time for you to verify. Go through the process. You know what the answers are supposed to be, right? Try it out. Okay, go through the process. Make sure you get the numbers at the end. Okay, and then I'm going to give everybody two more to try out. Okay, two more to try out after that. Okay, take your time. This has got a lot of just small little minor algebra steps, and sometimes not even algebra. Some of this is, a lot of this is arithmetic. Okay, so you know, don't be clumsy. Double check everything. Make sure you're carrying your negatives. Don't turn numbers into other numbers. All of those are common mistakes. Okay. Okay, moving on. Okay. So now that you know how to do the partial fraction decomposition, right? Now we know how to actually perform these integrals, right? So from before, right? We know what this is now, right? So this is equivalent to now the integral, right? I'm gonna put big parentheses here, right? Of 5 over x plus 2 plus a negative 3 over x minus 2 dx. Right? And we know how to solve these now, right? This is now equivalent to 5 ln x plus 2 minus 3 ln x minus 2 plus c. We are done. So notice how, you know, once we get the partial fraction decomposition, right? Once we get the partial fraction decomposition, the integral becomes very simple, right? Both of the integrals from above, right? The integral of 5 over x plus 2, you can do u substitution for that, right? And then the same thing for the other one. Okay. The next quick check has you guys doing the integral for the partial fraction decomposition from the one that you don't know the answers to from the previous quick check. So hopefully, right? Double check with your group mates, make sure that your partial fraction decomposition is all right. Okay, but I do want you guys to try it first. Cool. All right. So now what I want to do now is move on to repeated linear factors. So in the example that I showed you guys above, right? In the example that I showed you guys above, the partial fraction decomposition that I did, right, was just single term. So it was just, you know, x plus 2, x minus 2, right? Or an x plus 3, x minus 1. That was it. It never really took into account when you have a multiplicity of 2. So if you had something like x plus 3 and x minus 2 quantity squared, right? It never did any of that. It didn't handle any of that, right? So that's what I'm talking about when I'm for what we're going to do right now. Whenever you have factors that repeat, okay? So the way I'm going to do this is we are going to, without loss of generality, right? Okay, we're just going to look at a particular small example, right? And at the end, right, because the argument sort of holds water, the argument for more factors, right, sort of remains the same, okay? So let's go ahead and suppose that you had some p over q, right, where the p of x can be whatever the heck it wants, right? But the q of x is just, you know, a1x plus b1 times some a2x plus b2 squared. So the a2x, that second factor, right, has a multiplicity of 2, right? Okay. Since that factor has a multiplicity of 2, right, what that term can do, right, is that it can add two sort of separate fractions for that one term, right? It can add a fraction which just has the single power, and it can add a term that has the squared power. So the partial fraction decomposition becomes this: an a over the ax, a1x plus b1, b over the single, right? And then c over the square. So this is the only thing that really changes this, right? Okay. And if you don't do this, right, if you don't end up doing this, what's going to end up happening, and this is going to be your telltale sign that something went wrong, right? If you don't end up sort of doing this, right, what's going to happen is you're going to do a partial fraction decomposition, and at the very end, once you get your A, B, and C's, right, your partial fractions, right, they don't entirely reduce. They don't end up entirely reducing. Okay, which means that you have to go back to the sort of like the beginning and see what I missed, right? Okay. This is like the crux of the argument right here, okay? Because after this, right, it becomes a simple U substitution at the very end, and we, go on about our day, right? So remember how I said, right, this is for a specific thing here, right? This was just for one term that was multiplied twice with a multiplicity of 2, right? But if you take a look at the argument that comes right below it, it all holds water, right? Okay. So therefore, the generalized statement, right, is this down here. So suppose that you have a P over Q that expands to, the P of X doesn't need to expand, but the bottom one expands to some A1X plus B1 to some power K1. A2x plus B2 to some power K2. So each one has a different multiplicity, right? Okay, and hopefully this makes sense, right? There's going to be an A1 for the single term. There's going to be an A2 for the squared term, dot, 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 dot. A sub K1 for the kth term, because the multiplicity for that first term, right, is K. So each one of the powers gets its own special A, right? And then we move on to the next one, right? So it'd be B1 to the single power, B2 to the single power, BK to the K2 power. Does that make sense? All the way down, dot, 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 right? To the very last one. So it'd be Z1, single power, Z2, single power, Zn, single power to the kth power, right? And then at the very end, right, we can just integrate basically all of this. We get to integrate all of this right here. And it is, they are simpler integrals. You got to believe me on that one. Okay. So just to show you guys how this sort of works out, let me go ahead and do an example of what I'm talking about. Okay. So suppose we had this integral, right? I have to do the partial fraction decomposition, right? So it's an x squared minus 4x plus 11 all over x plus 3, x minus 1 quantity squared, that's an 11. So I have to break them up into the partial fraction decomposition, right? So a over x plus 3 plus b1 over x minus 1 plus b2 over x minus 1 quantity squared. Okay, and I'm going to rewrite. So the first two, I'm going to keep them the same. So it's going to be a over x plus 3 plus b1 over x minus 1 plus b2. I'm going to expand that bottom part. That's going to be x squared minus 2x plus 1. Okay. So now I am going to play around with this thing, right? That the fact that this, right, has got to be equal to this. Some A, B, and C. So we're now going to try to find our A, B, and C. Okay. So we're off to the races. If you take a look at the first one, right, A is missing the x minus 1 and the x minus 1 squared. but that's taken care of by just x minus 1 squared. So it's going to be a times x minus 1 quantity squared, right? And let me go ahead and use that expanded version. So squared minus 2x plus 1 plus b. The b, right, it's already got an x minus 1, so it's going to be missing another x minus 1 to make the square and the x plus 3. So it's going to be x plus 3, x minus 1, sorry, minus 1, plus b1, that was b1, right? And then plus b2, right? b2 is this one out here. I forgot the 2 here. b2 is already squared, so it's just missing the x minus 3, or plus 3, right? So x plus 3. And all of this has to be equal to x squared minus 4x plus 11, right? I'm going to expand out that left-hand side, right? A x squared minus 2ax plus a plus, if you expand x plus 3, x minus 1, you'll get x squared plus 2x minus 3. And then I'm just going to go ahead, well, let me just do it, shouldn't I? Right, b1 x squared plus 2x minus 3, right? I'm going to expand this to, now that this one's simple enough, right? Plus b2 x plus 3 b2. Okay, a x squared minus 2ax plus a plus b1 x squared plus 2b1x minus 3b1 plus b2x plus 3b2 has to equal x squared minus 4x plus 11. Now I'm going to group the a, b's, and c's, right? So there's an ax squared, b1x squared, right? And those are the only x squareds, right? So it's going to be an a plus b1 x squared. There's an x term here, an x term here, and an x term here. So that's going to be minus, so I'm going to do this, plus a minus 2a plus 2b1 plus b2 x. Okay, and then our last thing though is there's a number terms, right? So now I get plus a minus 3b1 plus 3b2 is equal to x squared minus 4x plus 11. Okay, so it turns out now, here's our set of, our system of equations that we need to solve for now, right? A plus b1 has to equal that 1x squared, right? A minus 2a plus 2b1 plus b2 has to equal to negative 4x, right? And then the very last one, a minus 3b plus 3b2, whoops, 3b2, has to equal 11. Okay, here are the system of equations that we need to solve for, right? So I'm going to leave that for you guys to try out. Okay, so try to eliminate A's and B's and C's as best you can, right? Okay, and if you do it right, the answer should be that A should equal 2, B1 should be negative 1, and B2 should be 2. Okay, so this is half the battle right here. Okay, this gives us the coefficients that are supposed to go up here. Okay, and that's exactly what we're going to do, right? So now I get to scroll down a little bit. Actually, no, I don't. Let me just leave it right there. So what we get now is this, that the integral right, of x squared minus 4x plus 11 all over x plus 3 x minus 1 quantity squared is equivalent to the integral, right, of 2 over x plus 3 plus negative 1 over x minus 1 plus 2 over x minus 1 quantity squared, all of that closed up, dx. Okay? So then that is equivalent to the integral of 2 over x plus 3 dx plus the integral of negative 1 over x minus 1 dx plus the integral of 2 over x minus 1 squared dx. All of these now are u substitutions, right? The first two are fairly simple. You're supposed to get something along the lines of 2 ln x plus 3 minus 1 times the ln of x minus 1. And then the last one is the weird one, right? The u is going to be x minus 1, right? And that's going to be squared. So what you get for this one is going to be equal to plus 2 times the negative 1 over x minus 1, and then plus c rounds it out. And we are done. Okay? Awesome. Okay, so the next ones are same type of deal, right? Notice that we can't do u substitution for either one of these, right? So we have to do the partial fraction decomposition. Okay? So I want you guys to try them out. Make sure you're double checking your numbers, right? Make sure you're double checking your process. Okay, moving on. Simple quadratic factors. Okay, there comes times, right, where your q of x, the bottom portion of your quotient, right, the bottom portion of your fraction, will produce terms, right, that are irreducible. In particular, the one that we're about to look at, right, is irreducible quadratic factor. So something like this or this, right? If you take a look at both of those, right, you can't factor it anymore. You can't get some x minus something times x plus something, right? Or the other way you can look at it is if you grab these two equations and you do the quadratic formula for them, they'll give you solutions, but the solutions are complex numbers. So that means you can't reduce them anymore. Okay, so what do we do with these? What do we do with these? And the answer to that is we handle them just like we did before. There's just one more caveat again, okay? So again, we're gonna simplify it first. We're gonna look at when a q of c, when the bottom of a q of c, q of x, when the bottom comes down to an irreducible quadratic factor, right? So some ax squared plus bx plus c where we can't reduce it anymore, right? And let's just say that it's squared, right? Then that means that the p of q, right? The p of q can be whatever it wants, right? But the q of x can now reduce down to this, right? And sort of we're collapsing two rules here, right? The power of the remainder of the division by just one of them, right, should be something linear. So basically, if I divide by my ax squared plus bx plus c, right, the biggest type of term that I'm supposed to be left with is something linear, some ax plus b, right? And then since it's squared, right, I have to get another one which also leaves the same type of size of a polynomial on top, right? So we now have four sort of coefficients, the a, b, c, and d, right? But the idea here is still the same to what was being done up above, right? So more generally again, right, suppose all of these are irreducible. right? Suppose that all of these are irreducible. Then there's got to be one for the first power, one for the second power, one for the third power, right? For just the first irreducible factor. And then there's going to be one for the first power of the second, right? One for the second power of the second, dot, 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 right? One for the K2th power of the second, and so on and so forth. I know it looks a little complicated, right? Don't worry. I think more than one irreducible quadratic factor to a power no more than 2 is probably the worst that you'll see, at least in class, right? I believe any more than that is sort of a war crime. It's a cruel and unusual punishment. Okay, so let me show you guys what I mean. Okay, so let's take this integral right here. Okay, so notice that this integral, this term down here, the x squared plus 1, right? That is now irreducible. I can't break it down anymore. Okay, so now I'm going to handle it, and I'm going to try to take the integral of this, right? Just by using the stuff that we've got, the process that I showed you guys up above, right? So we have this now, right? X squared minus x minus 2 all over x squared plus 1. All of this has to be equal to some a over x, right? Plus some b x plus c over x squared plus 1. Okay, I go ahead and do my common denominators, right? So what I'm going to have here is this a x squared plus 1 plus x bx plus c. All of this has to equal x squared minus x minus 2. Okay, I'm going to expand the left-hand side. A x squared plus a plus b x squared plus cx. Look at me go. I almost forgot a negative there. All right. I'm going to group all of my terms together. So it's going to be an a plus b x squared plus cx plus a has to equal negative x squared minus x minus 2. Okay, so now looking at this, I have my system of equations already. You guys see that, right? So a plus b has to equal negative 1. Okay, my c has to equal my negative x squared, so it's going to be negative 1. And my a has to be negative 2. Okay. And because of these two, right, we get the last one sort of for free. B has to equal to plus 1. So here we are. We have all our values, right? So therefore, my integral of minus x squared minus x minus 2 all over x squared plus 1 dx is equal to, right, the integral. Now I get to fill in my a, b's, and c's here. Okay, it's going to be, my a is negative 2, so minus 2 over x. Let me actually do the big one. Plus my bx plus c, so b is 1 and c is negative 1, so it's going to be x minus 1 over x squared plus 1 dx. Okay. This is equal to the integral negative 2 over x dx plus the integral. I'm going to split up this integral right here to this right here. X over x squared plus 1 dx plus the integral of minus 1 over x squared plus 1 dx. Okay. The first one, u substitution, negative 2 ln x. The second one, u substitution, Okay, let me run this one through. U is equal to x squared plus 1, right? So my du over 2. Whoa. So my du over 2 has to be x dx. And let me move that down a little bit. So equal to negative 2 ln x plus this right here is going to be a 1/2 ln x squared plus 1. Okay, and this should look like an original one of the identity functions, the inverse trig one. So this is going to be minus tangent inverse of x. And then we just add a plus c because that's what we got to do. And we are done. So notice how this section works out, right? It's essentially, we're leveraging the fact that we can break up, fractions, right? Into smaller fractions. And then that result gets used, we can use a u substitution to sort of, finish that up, okay? And I believe that's done. There are much more specific and written down strategies that can be found in the book. I don't see them as entirely necessary because like I said, anything greater than a power of 2, maybe 3, I consider a war crime, cruel and unusual punishment. Hopefully the online homework doesn't do that. I don't make you guys do that at all for your lecture questions. So just keep that in mind, okay? Besides that, I am done. If you guys have any questions on this stuff, please send me, drop me a line, come see me in my office hours or on my Friday times, okay? Like I said, I am done here. Happy studying.